This affects the image. The areas that will be impacted will indicate something in your burning eye. This area is excellent, meaning it is high, which indicates that it is higher than the rest of the brain areas that are not active. This is exactly what I observe in the brain, where there is an increase in the result due to an influencing factor, which I refer to as one that relies on having an influence that enhances this area. It is very quick, and they call it the bold technique. It tells you about the areas that are hyperactive or those with high oxygen supply. You want to benefit from this. Do you see the function of the part of the brain responsible for movement, or the stimulus or the reaction that will occur? Is it working efficiently or not? Do we understand? The bold technique, everyone. I said that I have two things, paramagnetic and diamagnetic. Paramagnetic means that I have free electrons present in the atom from the outside. What does that mean? It means I have iron atoms, which are paramagnetic. What does that mean? It means there are electrons. Here, meaning there are electrons everywhere. My atoms have two electrons next to each other in the last level, in the same corner, in the same square. So this will create a field, and this will create an opposite field, and the two will cancel each other out. This is called diamagnetic. But if I have an atom with a single unique electron, it will create a field in one direction without a corresponding opposite field. So I will have a magnetic field that changes and affects the external magnetic field, creating a magnetic field in all perfusion imaging. He works as a counsel to benefit them, and Jinn. In the perfusion sequence, let's focus on what I want to do in the perfusion sequence. I want to give a contrast agent to the patient. What does the contrast agent do? I mentioned this before. Does anyone remember Dr. Doa or Dr. Hala? Well, did anyone recover? The contrast agent used in MRI is called the contrast agent. What does the contrast agent do in MRI? All right, I understand what you're saying. Let's proceed with that plan and make sure everything is in order. If there are any issues, we can address them as they arise. Does that sound good to you? Gadolinium is considered, folks, as something you inject into the patient as a contrast agent that has free electrons or has 7 binding sites, meaning 7 binding locations associated with an element called DTBA. There is an empty space here that binds with hydrogen. What this space does is it binds with it and changes its magnetic properties. So when it alters its magnetic properties, it becomes in resonance. We need to pay attention to this phrase. With the media around it being in resonance means it doesn't move at the same speed, losing its energy, leading to faster relaxation for T1 and faster relaxation for T2. And the relaxation is faster for MXY. The MZ gives me a T1 visual representation, and the MXY gives me a T2 visual representation. So the presence of the contrast agent significantly reduces the T1 constant and the T2 constant in the molecular environment. Is that absolutely clear? Why does the presence of the contrast agent reduce the T1 constant? Because it causes the protons to spin more rapidly in accordance with the surrounding protons due to a change in the system. Reducing in T2 follows the same idea. It accelerates energy loss in the process, making the decay that occurs in the XY faster. This is the contrast agent. Let's focus on it together. I injected my contrast agent. I have two things. I always take the contrast agent for T1 imaging. I always see if the tumor is illuminated or not in T1, if I am using the contrast agent. Why glow? Beautiful. So what will the vascularity do? As you know, it will indeed deliver the contrast agent very significantly to the tumor, right? Exactly. Keep the MZ of the tumor. It will happen quickly, as expected. Right. How am I considered a visitor among you guys? Okay. All right. Let's focus, everyone, please. Here it is. Here is the MZ. I injected a contrast agent. Did this contrast agent make the MZ of the tumor return quickly or slowly? Quickly. It remains to return quickly like this. As for the other tissues, they are much slower. You stand here to record which one has the highest signal, which one has the highest brightness, where the tumor is, right? The tumor will be more bright. So we understand the brightness game. You are standing to record. This contrast agent made it fast because it has the contrast agent returning, so it became high. When you come to record, yours, it is very high, the highest one compared to the surrounding tissues. Great. Now let's talk about the tumor, which is expected to descend rapidly, will do so quickly, right? When compared to the other surrounding tissues. Which one of them has a higher mix of components? Assuming T1, T2 in the tumor. God bless you. So if the other tissues are indeed higher, the signal from the tumor will either be suppressed or bright. If it actually happens in T2, then fine. But the image that will come out will be different from T1. It will be dark in T2. Why is it dark? Because you did it in T2, so your MXY is weaker than the rest of the tissues, which will give you this. Is this clear or is there a problem? The curve? Yes, doctor. The curve should go down like this. Your contrast agent will reduce T2 or increase it. So what does it mean to reduce it? It means it will drop quickly to 37% of its value. Good. It used to take time to reach 37%, but now it will drop faster. This time will be shortened. So this is T2, right? Therefore, I have very essentially reduced it. Now let's consider magnetization. If we assume that the rest of the tissues are the same, this is the tumor. And what about the other tissues? Which one of them has the lowest magnetization and which one has the highest? The tumor with the lowest MZ is the one with the least among them. This means that if I want to measure at a certain time, I can do so. Look here, this is a tumor. And here are the other tissues. I want to measure here at this time. Is this value high or low? Lower? Lower? So it's lower for the tumor. The tumor will have a weak signal for me. Now, if I take my perfusion scan, I take a quick gradient scan, and I take images. These images tell me about a specific location before the contrast agent supply and after the contrast agent supply and after the washout. I measure the T2 signal, not T1. So focus with me, everyone. I will take a specific point in the brain and say I want to see the shape of the signal at this point. Before injecting the contrast agent, while I'm injecting the contrast agent, and after the contrast agent washout, let's focus. Here is the image. Is T2 illuminated or not? Great. The waiting signal, doctor. So, is this image normal or does it have issues? Great, I just injected my contrast agent. What happens to the signal now, doctor? Is it high? It was high before, but why did it drop? It dropped because of the injection of the contrast agent. After that, what will happen to the signal? Will it come back up? Great. May God bless him, because there will still be contrast agent present. The contrast agent in MRI lasts for a long time. Now the question is, can I study the hemodynamics of any organ or tissue I want using perfusion imaging, or can I not? This is what I'm doing, guys. This is the perfusion. You take a fast sequence on a specific organ. You take it before the contrast agent and during it. For example, every second, you take an image of something and it gives you the hemodynamics for those organs. No. Ha 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 ha. The best contrast agent is available, and the washing out is the best contrast agent available, and the washing out. No, the contrast agent will exit now after it has been absorbed. This contrast agent exits the body. So when it exits the tissue, does it have to go back out again? Yes, doctor. I am currently taking an image from the signal. I am taking an image from the tissue. I am getting a signal from it, okay? Before I inject the contrast agent, my signal was very normal. Right? So, what happens to the contrast agent? This contrast agent reduces the T2. This is understandable. We said it correctly, right? No problem. So, the signal decreased. Now, my contrast agent has started to exit from the tissue itself. This is normal vascularity. Do you understand me? It means that either a contrast agent is injected into any person or anything that exits from the kidney. So there must be a washing out from the tissue through its blood flow. The circulation continues normally. So when it exits from the tissue, will the signal intensity increase or decrease? It will increase. Why will it increase? The effect of the contrast agent is gone. The contrast agent was reducing T2, and when it moved, T2 returned to its original state, which increases its duration. So my MX1 started to grow. It's here. Yes, that's right. This is the form known as dynamic scan contrast, which captures perfusion, allowing you to see the plot flow or observe the dye moving through the tissue. They always use a sequence called ecoplanar imaging or ecoplanar sequence in this context, which is considered an ingredient sequence in this subject. It remains a very quick examination that takes multiple equal values and observes the flow of the dye within the organ or tissue you want to study. For example, this curve shows that I am taking a lesion, and you can also study it at the level of the region of interest. Here, for instance, you want to see how the plot flow looks in this area. This area might have a different flow compared to another area, so you can see how they differ. Sometimes they also study cases here. For example, look here, this happened in this location. I want to show you, for example, suppose we are not going to talk about T2, but rather about T1. How would the previous situation look? If we turn the situation bright, yes, it would be bright. Would the curve rise or fall? God bless you. It would rise, because at that time, a decrease in T1 means that the signal is brighter. This means that the signal is more bright for me regarding the signal when you are not in T1. Okay, Now let's just talk about the last thing and the most difficult thing, just a little bit. So what's the topic of spectroscopy? I was just talking a little while ago and mentioned that all the atoms I have exhibit precision frequency. This means that every atom in the world contains protons. Protons are found within the nucleus, and this nucleus exists in all the atoms in the world. Therefore, any compound or atom you can imagine must contain some protons. It must have protons. What does this mean? It means I can excite any proton in any material. I can receive a frequency or a signal from a proton present in creatinine, for example, or in choline. These substances I keep mentioning are very important as they provide information about my pathology within the body. For instance, if I have a tumor, this tumor, the result is that a specific pathology or problem increases the concentration of certain metabolites while decreasing others. If I can determine the concentration of the metabolites present in my pathology, it gives me an indication of the type of problem. Additionally, if I am monitoring the situation and it worsens, knowing what is happening inside is very important. So, how do I do this? I want to obtain information not just about the metabolites inside. Understanding this is crucial. I want to get my signal from this metabolite. Not just that. The water is not the conductor, but the most significant thing giving me a signal is the water. When we look at the shape of the signal coming from the signal intensity, this is the signal intensity on the y-axis, and here they call it parts per million, which is the chemical shift I will talk about shortly. The shape of the signal that I always receive, which I rely on in my image, looks like this. This is the signal for fat, and this is the signal for water. So, which one has a higher intensity signal, fat or water? All the signal intensity of water is higher than the signal intensity of fat, which is nice, but there is a difference between the two. What do I mean by a difference? I call this difference a chemical shift, which we talked about a little while ago. So this difference is called a chemical shift. Now, what is the difference between the frequency of water and the frequency of fat? The hydrogen present in water and the hydrogen present in fat. Now, the metabolites that are present in my pathology are all located in which area? The water and fat signals are all here in this place. Are their signals weak or strong? Weak. So how do I take the metabolite signals, analyze them, and produce a spectrum? You need to eliminate the water signal. How? By knowing the frequency of the water protons and giving it an RF pulse before. You start the MRI spectroscopy. What happens when I give it an RF pulse? Do you remember the saturation topic I was talking about? I said that I can give saturation, and this saturation will eliminate the hydrogen present in the water. In this case, I will start applying the sequence for MRI spectroscopy. Now, I will work on the metabolites, and this is very important. The spectrum will appear in this form. This spectrum always has a distinctive shape. The tumor or neurons, the nerve cells, contain a substance called N-acetylaspartate. Its curve is usually very large, or in normal conditions, it has this curve shape. So, N-acetylaspartate is the highest thing present. This is the normal shape. The concentration of N-acetylaspartate, creatinine, and choline are the three metabolites that give me a clear indication of my pathology, where its localization is, what type it is, and what its condition is. I have already lost the water that was covering this information, so I find that the N-acetyl aspartate has a very high peak, the highest one, while creatinine and choline are next to each other. Now there is a difference in frequency between N-acetyl aspartate and creatinine and choline. I call this difference parts per million. The parts per million indicate how much difference there is between the frequency of N-acetyl aspartate and creatinine. It doesn't mean its value. It's like saying I have this much difference. It doesn't mean the frequency value itself. For example, here I have the fat and the lipids or water, and my lipids are important. There is a difference between them of about 220 Hz in frequency. The lipids or fat rotate faster than water. The difference in the chemical shift is called 3.5 parts per million. What does that mean? It means on this scale, the frequency of the lipids here is, for example, 1.5, and the high scale is 5. So the difference between 1.5 and 5 is 3.5 parts per million. This is the difference between the peak of the lipids and water. This difference of 3.5 parts per million, when multiplied by 64 megahertz. What is 64 megahertz? It means I have a 1.5 Tesla device that makes the protons rotate at a speed of 64 million hertz. So when I multiply I have the difference that I mentioned between fat and water, which is 3.5 parts per million. This is because the peak for fat is at 1.5 and the peak for water is approximately 5. So the difference between the two is 3.5. When I multiply these 3.5 by the frequency, when I strike them at a frequency value of 64 megahertz, which relates to the 1.5 Tesla device, it gives me a frequency of 20 Hertz. So this means 3.5 parts per million. The same thing as I said, I want to eliminate izalatul ma completely. Once I remove the water, I will have alanine, creatinine, and choline, which are the compounds I am working on. Now you have, for example, aspartate, because aspartate is the Na, which is the big peak I am talking about. Where is this first one found? It is found in the neurons, in the nerve cells. If there is a tumor or a specific disease, this tumor causes you to lose neurons. So, do you expect that when there is a loss of neurons in the nerve cells, the concentration of NAS will decrease or increase? It will decrease. All right. In cases of hypoxia, or when you have a mart nexi asabi, or a worm, or any issue affecting the neuronal cells, we will find that there is a change in the concentration of aspartate. So, the curve that I have, instead of being large like this, starts to decrease, which is a sign of a problem. This indicates that there is a problem or a specific pathology in this patient. Now let's talk about creatinine. For example, the same idea typically applies. If you have a very high grade of estrod, cytomas, it starts to show in its signal. Creatinine is one of the distinctive things, as its normal peak is very close indeed to choline. The two are very close to each other, and here is aspartate. This gives you an indication of a specific issue, and these give you an indication of other things. So, each one of them, or the peak itself, looks like this. This gives you an indication that there is a problem in the pathology, so rely on how the peak or signal intensity looks. When the concentration decreases, the signal intensity decreases. When the concentration increases, the signal intensity increases. Okay, let's move on to the most difficult part. I have something called the الطيف الأحادي للفوكسل and the الطيف المتعدد للفوكسل. What does this mean? It means that when you come to perform the spectroscopy, you select your region of interest, like in the case of this meningioma, for example. Then you create a square and tell it to perform the spectral analysis in that square. How does the curve come out? Here is the alkalinina, and here is choline. You can see that the shape of the curve changes, right? So the question here is, how does this curve come out? And why doesn't it give me the signal from the entire brain? I mean, why do I choose how I can focus on a specific area and tell it I want the spectral analysis for that area only? I can also choose another voxel in a normal place and say this is its spectrum, like here, for example. Look, guys, yes. How does my device select voxels? Let me explain to you, for example, in a simple way, to make it clearer and easier to understand. First, I am dealing with pixels or voxels. So, I currently have this brain, and I have a tumor, and I want to measure the metabolites present in this area. Am I treating this image as 2D or 3D? Are you working with it in the X plane or in the XYZ plane, or X and Y?